So introducing our next speaker, Dr. Diana Zivak. Diana is a senior geologist with the Geological Survey of South Australia with over 10 years of experience in the industry and academia. Her background has largely focused on using mineral geochemistry to detect distal footprints of mineralised systems, and in her current role she is focused on understanding the rare earth element potential in South Australia. Welcome, Diana.
Thank you, everyone. Today I'm going to be presenting some work we've recently done since basically June this year on rare earth element potential in South Australia. And before I go on, I'd like to acknowledge all of the people in the critical minerals team that have contributed to this project, and particularly Mitch for taking on the carbonatite mammoth story. So as the title says, the aim of this project is to map the prospectivity of South Australia. And this is basically done through using legacy data, existing geochemistry, and new data we're going to acquire through core logging, sampling, and fieldwork. Now, when we started this project, there were a number of questions that we didn't know. First of all, we didn't know what are the different types of rare earth deposits in the States. Do we have a complete list of occurrences in our database in South Australia? Are there elevated occurrences of rare earths associated with different commodities? What are the ages of the mineralization? What are the main tectonic drivers? Which area is most prospective? And so on. And I'm sure there's more questions that are going to come up as we do this project. So I'll just quickly run through some of the main deposit types of rare earths. Firstly, I'll start with magmatic-related rare earths because they're the globally most recognised, things like carbonatites, alkaline igneous rocks, pegmatites, and so on. Exemplified by Mount Weld mine in WA. The more, I would say, more enigmatic hydrothermal rare earth deposits that can occur with or without magmatic or hydrothermal input, and these include your sort of vein and breccia-hosted deposits such as IOCGs, or unconformity-related rare earth deposits such as Browns Range further north, sort of up in here, which has got no magmatic hydrothermal input at all. Next we go to sort of placer deposits, and these are your heavy mineral sands and channel and alluvia placer deposits. Sedimentary deposits, and these deposits are currently not produced in Australia, and they include things like rare earth rich phosphorites that are exemplified by the Georgina Basin in northern Australia, coal and coal ash rare earth deposits, and I guess a new type that I've named that may or not be true here in South Australia, particularly in Adelaide Super Basin, the diapiric breccia associated rare earth deposits. And last but not least, of course, the superficial weathering deposits, which are exemplified by clay-hosted rare earths and residual laterite deposits. Now, if you want to look at occurrences in South Australia, of course, you'll go to our database, MINDAP, and you can search by either by the commodity up here, which can be your rare earths or heavy minerals, for example, and different rare earth elements if you want to search by mineralogy, so you can use any one of these minerals and in the search database to find those. After you do that and you remove duplicates, you end up with about 99 occurrences in South Australia, and that excludes the heavy minerals, of which there are about 120 or so. So what does it look like on a distribution? So when I first started this, I thought I'll map all of the occurrences by their type, and this is the resulting map. So this is what you get if you do a search by commodity. There's a few more occurrences if you search by presence of a mineral that's rich in rare earths. And then at the end, when you add heavy mineral sands, the picture's looking a little bit better in terms of occurrences. Now, what I thought I'd do is I thought I'd compare the different deposit types that occur in South Australia with those that occur globally, and two things kind of struck me. First of all, we seem to have a lot of the vein and breccia-hosted type deposits, most likely associated with the IOCG systems, which is only, in South Australia makes about 48%, and globally, there's only 3% of those deposits that occur. But globally, we have a lot more carbonatite and alkaline type of deposits. In South Australia, we currently don't have any definitively defined carbonatites or alkaline deposits or occurrences. And Mitch can talk to this a bit more if you want to ask him more questions about it. But I will say this, do we have a high potential for these kind of rocks in South Australia? Now this map is a carbonatite potential map that was produced by Geoscience Australia in August this year. And what it shows is there's high potential for carbonatite in South Australia. As Adrian rightly pointed out, we should be tripping over them. But we still have to do a lot more work to find carbonatites in SA or to define them. In terms of alkaline rocks, there seems to be potential to the east of the state. There's two occurrences, the two little triangles here is the Ugalima carbonatite, potential carbonatite, and Wallaway as well, which is again still being determined whether it is or not a carbonatite. So the potential is there, and I'll pass you to Mitch if you want to ask him questions about it later on. Now, I thought, well, let's have a look at the geochemistry of the state. And our SARIG map online platform is really good for searching geochemistry. As you can see, if you scroll down, you can go to view geochemistry. You can create your custom data download. You can enter your analytes, and you can search by source type where you wanted to have a surface samples or say subsurface samples, including drill core. You enter your email and you request download. It's as simple as that. So for looking at geochemical prospectivity of the state in terms of rare earths, I decided to use lanthanum and cerium only. The reason for this is because a lot more samples are, particularly legacy samples, do not analyse the full rare earth element suite. They only use lanthanum. They only analyse lanthanum and cerium. So we can have a better coverage if you just use lanthanum and cerium. I rejected some samples with less than 0.01 ppm due to detection limits, and also samples that have really high cerium values in the surface samples, because they may actually reflect oxidation state of cerium and not the full rare earth element suite. This is just a list of codes that you can use in the SARIG map to search for the surface or subsurface samples. And when we do this, we get over 600,000 samples. Now, is lanthanum and cerium a good proxy for total rare earths? I believe it is. As you can see in this image, I plotted the lanthanum and cerium against the other middle and heavy rare earths, particularly the ones that are most desirable for the industry. And there's a strong positive correlation which suggests that if we have high concentrations of lanthanum and cerium, we should see high concentrations of all of the rare earths. Now, when we plot this on the map, you can see there's quite a few occurrences that are quite high. Now, I guess yellows are the most interesting. From yellow to red are the most interesting ones. But if we plot the occurrences on top of that, we can see that they cover pretty much all of the ones that we see, but there are also some occurrences here that are not mapped currently in our database that need a closer inspection. So yeah, we need to look into this in a bit more detail. So it's a big challenge to try and map the prospectivity of the state using geochemistry. So we thought we'd start on a province by province basis. And these are the 4 provinces that we selected from Curnamona, Alay Super Basin, the Gawler and the Musgroves, basically all of them. So yeah. Anyway, let's start with Curnamona. So first part of this project, I decided to focus on the Curnamona and map the occurrences of rare earths in the Curnamona. As you can see, they concentrate in the northern and southern parts, and that's mainly because the rest of Curnamona is kind of covered with a thick sedimentary cover. And this is also reflected in the geochemistry. You can see some high occurrences there of down south in the north of the province. And if we plot occurrences on top of that, you can see that yes, we've got a lot of them, but there's some that haven't been looked at all. So this is where I started. I thought I'll go to the south of the province and I'll have a look at what's going on in the southern part of Curnamona. And this map shows the drill holes that have, to date have been examined in these sort of yellow circles. They have been logged. We have sampled them for whole rock geochemistry, petrography, and geochronology. And during the logging, recognised mainly two types of mineral systems associated with rare earth mineralisation. The first one is uranium and rare earth mineralisation that's associated with granitic intrusions and hydrothermal alteration of the Williama supergroup, and they're metasedimentary rocks. And also copper-gold mineralisation that's associated with elevated rare earth elements, and that's exemplified by these prospects, the Croziers, Calcarew and Portia, which you might have heard of previously. I'll start with uranium rare earth mineral systems, and particularly the Mount Victoria prospect, which is quite interesting. Now, Mount Victoria prospect was originally a uranium prospect that got high concentration of davidite as the main commodity mineral. And legacy data suggests there's also other rare earth minerals such as zircon, monazite, and xenotime in this prospect. There have been a total of 5 drill holes that have returned really good results, and these are available in the core library if you want to look at them. Some of these have over 2 weight % total rare earths, which is quite good, but on average, they average about 0.83 weight % over 3 to 10 metre thick intervals. If we look at the downhole profile, there's 2 things I want you to take away. Firstly, that the uranium rare earth mineralisation also seems to come with some higher concentrations of some of the other critical minerals like niobium, vanadium, zirconium. Cobalt is a bit more patchy, as well as copper. So the copper system in here is not as prominent, but also that these have these sort of black kind of shades, these magnetite pyrite-rich zones that seem to have a close relation with the mineralisation. If we actually have a look at the rocks, because I had to show photos of rocks, I'm sorry, we can see this is the Williama supergroup metasediments. They have this pervasive gneissic foliation. They're rich in biotite, quartz and felspar, and cross-cut by late muscovite fabrics. As you get closer to demineralisation, the fabrics are still there, but you start to see these biotite-rich sort of zones and veins cutting across the main fabric. You start to see these brown minerals, which I think might be rutile, but I'll wait for thin sections to confirm that. And then as you get into the main mineralized zone, the actual fabric completely disappears. You see now the appearance of davidite, which is these sort of metallic kind of crystals, in biotite matrix with these quartz and felspar wispy kind of clasts. And as you go sort of further down the mineralization, you get into really highly brecciated metasedimentary rocks that have matrix that's rich in pyrite and magnetite surrounding these clasts. So that's quite interesting. Don't ask me why yet. So magnetite and sulfides, mostly pyrite, but also occasionally bornite and chalcopyrite are typically associated with these uranium rare earth zones. Within these rich high-grade zones, magnetite usually disappears. As you can see in these sort of profiles here, the blue is the magnetic susceptibility. Not sure why that happens, but it's an interesting problem to solve. But what's really good about this prospect is that it's got really high concentrations of heavy rare earths, which is not typical of, say, carbonatite type deposits. So heavies are probably more desirable in many ways, and as exemplified by the ionic absorption clays in China, they're heavy rare earth enriched. So this is quite an interesting prospect to look at. Now the copper-gold rare earth system, I'll use an example of the Crozier prospect. We found 1 drill hole, which is an RC chip drill hole, and only lanthanum analysis was available for this prospect, but you can see lanthanum values as high as 8,000 ppm, so just lanthanum. And some of these have, average is over 2,000 ppm lanthanum over 36 metres, which is a pretty good incept. If you look at total magnetic intensity, you can see, I think you can all guess what the big round thing is. That's the intrusive magmatic suite of Bowery suite, which intrudes into the Curnamona group, or the lower Williama supergroup metasediments in yellow. And where these faults cross-cut these metasediments, it seems to concentrate where the Crozier's prospect is. Now, what the relationship is still unclear at this stage. If we look at the downhole profile, Again, we see this zone of elevated rare earths, copper, cobalt, and again, iron is quite high in these zones as well. So there's a close relationship between the possibly magnetite, hematite, and sulfides with rare earth mineralisation. So in terms of the mineral system at the Curnamona province, a majority of the prospects seem to be linked closely to the main intrusive bodies of the Bimbawi suite, but they seem to, particularly in the south, post that the main Olarian orogeny, but we will have to confirm this using geochronology. First pass logging suggests complex mineralogy closely related to these systems, and there's a close spatial and possibly temporal relationship between hydrothermal magnetite sulfide and uranium rare earth mineralisation. So more information to come in the next few months. So where to next? This is just the plot of the highest intercepts and the zones of which we're trying to focus, mainly the Gawler and the Musgraves. And what we hope to achieve at the end of this is we hope to have a better understanding of rare earth mineral systems in South Australia, as well as the mineralogy to better assess the economic availability of extraction of rare earths from these deposits. We hope to have some geochronological constraint on when these rare earth forming events happened, as well as a comprehensive report will be released sometime next year. I put May 2024, so yeah, I can do it. Thank you.